phase and magnitude conditions are two essential conditions that we have for the Root-Locus approach. And over here we are going to define them. So if you remember, the characteristics equation that we have for the closed loop system could be written in this form: d plus rho times n equal to 0. Now if we divide both sides, let's say, with d of s, we can rewrite it in the form of 1 plus rho times n over d equal to 0. Maybe let me write it over here again. So d plus rho times n equal to 0. If I divide everything by d of s, we will get d over d, which is equal to 1 plus rho times n over d equal to 0. And we already know that this n over d indeed could be denoted as g prime, where we have the gain taken out, okay? So 1 plus rho times g prime of s equal to 0. We can also rewrite this in the form of, I can take 1 to the other side, so rho times, let's use another color, rho times g prime, which is equal to n over d, is equal to minus 1. Then g prime, which is n over d, will be equal to minus 1 over rho. So basically this is the characteristics equation for the closed loop system. So n over d is equal to minus 1 over rho. And we know that rho takes real values, okay, from minus infinity to plus infinity. Now, all the points of the complex plane which satisfy this equation, and indeed any of the equations that we had, because they are identical to each other, any point on the complex plane which satisfies this equation, it will belong to the Root-Locus, because it will be indeed a pole of our closed loop system, that point. If we take the last equation into account, so n over d equal to minus 1 over rho. We know that rho is a real value, but for n of s and d of s, we have s as a complex value in general, yeah? So if we want to have this equality for a given value of s, we need to have the amplitude of both sides being equal to each other, and also the phase of both sides should be equal to each other. So we will have amplitude of n over d being equal to amplitude of, let me write it again over here, should be equal to amplitude of minus 1 over rho, and this could be written in the form of 1 over amplitude of rho. We just take the minus sign, yeah? And this gives us the magnitude condition. The next condition is the phase condition, and it says that the phase of n over d should be equal to phase of 1 over minus 1 over rho. So this is quite important, the phase condition. I would say it's more important than the magnitude condition. So phase of n over d should be equal to phase of minus 1 over rho. When rho is bigger than 0 for the positive locus, so phase of minus 1 over rho for rho bigger than 0. If rho is a positive value, minus 1 over rho will be some negative value. Okay, so this will be negative. And therefore the phase of minus 1 over rho will be an pi plus minus 2h pi, because it's a negative value, yeah? If this is the s-plane, it will be located somewhere here. minus 1 over rho, and we can see that if I want to find out the phase, I just connect that point to the origin, and then this will give me the phase. And obviously we can add or subtract multiplies of 2 pi from it. For the negative values of rho, when rho is smaller than 0, then phase of minus 1 over rho will be phase of some positive value. Okay, so let me say that this will be bigger than 0. The point will be located in our S-plane on the real axis on the right hand side, and if I want to find out the phase for that point, I will connect that point to the origin. I will draw a horizontal line from origin towards plus infinity, and you can see that the angle which should be obtained over here will be equal to 0. Okay, so the phase will be equal to 0, and we can add multiples of 2 pi to it. So for negative locus, it will be equal to 0 plus 2h pi. In general, we say 0 plus minus 2h pi if you consider only positive values for h. So this is the phase condition. Phase of n over d will be equal to pi plus 2h pi for rho bigger than 0, and 0 plus 2h pi for rho smaller than 0. The phase condition will determine whether a point belongs to our Root-Locus or not. If it belongs to our Root-Locus, then using the magnitude condition, we will find out the proper value for rho. So once a point S satisfies the phase condition, we can always find the value of rho such that the magnitude condition is also satisfied. Indeed, with the magnitude condition, we will find the proper value of rho. For the phase condition, we have the phase of n over d. We can define it. Phase of n over d indeed could be written in the form of phase of n, which is numerator, minus phase of d. And then phase of n, so n of s indeed gives us the zeros, yeah, of the system. Okay. For phase of n of s, we can find out the phases that we get from zeros, and then they will be written in the form of sum of phi i's for I starting from 1 to m. Keep in mind that m is the number of zeros of the system. And then for d, for the phase of d of s, we will write it in the form of sum of theta i's for I starting from 1 to n, where n is the number of poles of GP of S. Okay, so it comes from the open loop system. Therefore, we need to find out, in order to obtain the phase of n over d at a given point at S star, let's say, at S star, we need to find out the phases coming from the zeros, add them to each other, and then find out the phases coming from the poles to each other and subtract them from the addition of the phases coming from the zeros. So we need to find out phi i's, add them to each other, theta i's, add them to each other, and then subtract these two from each other. Over here we have an example. We have a system in which there are several number of poles, as shown here, and a single zero. And we want to find out the phase of GP at a test point like S over here. The trick in finding the phase of GP is to find out the phase contribution from the zeros. Over here we have a single zero, which is denoted as Z1. So we just need to connect it to this test point, and then draw a horizontal line from that 0 towards plus infinity, and over there we will get the phi value. So phi 1 is obtained over here. Okay, so we have phi 1. Then we find out the phase contribution coming from the poles. For the pole over here P1, similarly we connect it to the test point. We draw a horizontal line towards plus infinity, and then we find out the phase between those two lines, the angle between those two lines, and we will get theta 1. Theta 2, theta 3, and theta 4 are obtained in a similar way, and then they are written over here. So phase of GP will be equal to phi 1 minus theta 1 minus theta 2 minus theta 3 minus theta 4. For the same system, at another test point, S star over here, the phase is again evaluated. So you can see how it is evaluated for the 0. Again, the 0 is connected to that point, to that test point. A horizontal line towards plus infinity is drawn on the real axis, and over here we will have phi 1. And similarly for the poles, we have theta 1 obtained in a similar way. For theta 2, the pole is connected to the test point, and the horizontal line from the pole towards plus infinity is drawn, and then we have obtained theta 2 over here, and similarly for the other poles. And we have the same indeed equation for finding the phase of GP. So depending on where the test point is, we will apply we will find out the phase contributions coming from the zeros and the poles, and then we will have the simple calculation of sum of phi i's minus sum of theta i's. If this is equal to, in general, phase of minus 1 over rho, if we have this equality, that test point belongs to our root locus. If this equation over here, this equality doesn't hold, then the test point doesn't belong to our root locus. When we go through the examples, this will become easier for you you will learn how to find out the phase contributions coming from any of the poles and zeros. So we will do this manually indeed. In the next lectures, I will help you to learn how we can do it manually. It will take some time, of course, and some efforts. At the same time, we can also use the MATLAB. The MATLAB provides us the RLocus command. You can pass the transfer function to the RLocus command, and that will automatically generate you the root locus plot of the system. We also have the RLTool command. You can use it later. It's also quite a useful tool. It will help you to design the controllers later. Okay, so later on we will work with the RLTool. So working with the MATLAB will be quite easy. Let's say you will just give the transfer function to MATLAB, and it will give you the root locus plot. However, if you start to learn to draw the root locus manually, if you learn how the root locus is obtained, you will have more understanding in terms of how the location of the poles of the system change when you modify, let's say, the transfer function. If you add a 0 or if you add a pole to the system, how the root locus of the system is going to change, and how you can use this in order to design a proper controller. So this will give you some experience in terms of, or let's say it will make you ready in order to be able to synthesize or design a controller. Okay, so we are going to do this manually, even though we have tools which are provided by MATLAB. Anyways, you can always do it with MATLAB as well, and then compare what you have obtained manually with what you can get from the MATLAB in order to verify your work. In the next lecture, we will go through some rules or properties that we have for the Root-Locus, which makes it possible to draw the Root-Locus plot for a given system with a given number of poles and zeros. Thank you for watching this video lecture, and see you in the next lecture.